So this is a 4-bar mechanism in which the second and fourth links are, well, have negligible mass. We don't care about them. It's of course a simplification for the problem. And the third link has a certain mass of 0.6 kilograms. The dimensions are given. The angular acceleration of link 3 and its acceleration of its mass center is given so that we can find the inertia forces. Okay. And once you find inertia forces, actually the problem becomes a static problem. By the way, let me just, there is a small error here. This should be 100 degrees. Okay. I have drawn the free body diagrams the last time. For these two links, it is this is a two-force member. This one is a two-force and a moment member. And this is a three-force and a moment member. Link 3 is not standard. So we will write the equations, equilibrium equations for these members, including the inertia forces. Inertia forces are included. So let's write for start and write for the links, the equations for the links. Okay, so for link 2, the forces in the x direction is, by the way, yes, F2, 3x minus equal to we take counterclockwise as opposed. This is for link 2. We could also use the fact that this is a two-force and a moment member so that we could have put them in the same direction. Although we wouldn't know the direction, we could have put them together. But we just write the equations in this case. And for link 3, is in the minus direction. This point B. And let's call this distance B3, 9, 60 degrees, right? Plus I3 equals 0. This is coordinate 3.
Hocam bir şey sorabilir
Evet.
miyim? 30 eksi 60'ı nereden bulduk acaba? Nasıl bulduk?
This 60 degrees theta 1, 3, this is given. This is also given. The angles are given.
Tamamdır hocam. Çok teşekkür ederim.
For the link 4, well, it's a two-force member actually. Let's say that this is length is A4. All these are given actually. This is 0.088 meters. This A3, A2 is, what was it? 40 millimeters, which is 0.04 meters. This is 6, 8 meters, and A3 is 100 meters, which is 0.1 meters. Okay. This was O4, as you might remember. Taking moments about O4 is this is this. So this is F, not 3, 4, F4, 3. Okay. Okay. Well, we have, G14s and so on, but we don't need those G14s, so this much is enough for us. For example, these can be written as follows. This one can be written as it is a minus because it goes to the other side, sorry. So, okay, and for the third equation, these things are this is known, so you can write this. And A3 is known, A3 is known, B3 is known, Fi3 is known, Ti3, these are all known, so that you can write them. And what you get out of this is 0.0866 F43x plus 0.0. One volts, 21, 6. This torque equation gives you the following equation. And this one gives you that F43y equals A force cancelled here. F43 x tangent to the minus sign. So you see, let's say that this is equation 1 and this is equation 2, so that we could F43 equations, only two equations with two unknowns. So solve 1 and 2 together to get And from here, let's call these equations A and B.
Hojam, you've written F43x as 0.574 and F43x as 3.25.
The other one has to be Y. Yeah, that's right. This is Y. Yes, that's right. Thank you. So F43x is known here so that we can find this one. This goes to this side. Minus sign means that the direction is opposite, okay? F23y equals from here, from the equation, this goes here, this goes back, so this is positive. 5.82 plus 9.42. Okay,
Hojam,
yes.
can I ask about the torque equation? How did we get the torque equation?
Third equation. Which one is the third equation?
The torque equation or the
Torque.
torque? Yes.
Which one? This one?
Yeah, TI3.
TI3. TI3 is the inertia torque. The inertia was given. Well, this is last time we talked about this. TI3 was the I3 times, I3 is the inertia of the third link mass moment of inertia times alpha 1,3. Alpha 1,3 is given. I3 is given. So we multiply them to get the torque. Inertia torque. Okay.
Yeah.
If alpha 1,3 is clockwise, the inertia torque is counterclockwise. Okay?
Okay, Hojam.
Okay, F23y. Now we want to find the T12, as you know. What is that? T12. Here, from this equation, T12 is simply let's call this equation C. From C, T12 is equal to minus A2 F23y, which is 1. A2 is given as 40 millimeters. Minus 0.04 times 59.4. Newton millimeter. But there has to be a minus sign. Minus sign means that it is clockwise. Okay. like, so this is the result. Okay. So, so much for this problem. Do you have any questions about it? This was actually an exam problem I had asked some years ago. You know, it is manageable in during exam time, like half an hour or 40 minutes or something like that. Okay. If you don't have any questions, this will be it for the dynamic force analysis of mechanisms. I will start a new subject, the vibrations, the vibration analysis. Which is, you know, the last part of this course is vibration analysis. So let me start a new board. Like vibration analysis there. Now, what do we understand from vibration? It is vibratory motion. You know, it is a motion like, if you take this as the time axis, the motion that repeats itself is a vibration. This is what we call a vibration. A motion that goes back and forth is vibration, for example. A typical vibrational motion would be this: a mass and a spring. Okay. This is the displacement x. You pull your mass a little bit, let's say, and your mass is going to make the following oscillation. Over the time, x versus time. But if you have a plotter, you can plot this. So there are many, well, vibrations you see in lots of mechanical devices. Some are beneficial, most are not beneficial, but we see them all over the place. Anyway, let's have a definition of it. We call vibration as the motion about an equilibrium point. For example, for this case, it is just moving back and forth where this is the equilibrium point, okay? Here you have the equilibrium. Whereas a dynamic motion is not might not be vibration, it might be just going, you know, from one distance to another one. That wouldn't be a vibration, but vibration just is oscillation, basically. Well, what are the causes of vibration? Let's talk about this a little bit. You know, it might be an unbalance in the machine that is a force creating unbalance. It might be wind might cause a vibration because of its vortices. You might have rough roads which cause vibration in the cars. You might have like earthquake, which causes vibration in the buildings, okay? And some external forces might cause the vibration. So there are some external forces in the machines or devices that cause the vibration. Usually they are not very beneficial, okay? So the results of vibration, as we might say, is like things like noise, wear, and fatigue of the machine elements. And these are usually not very beneficial. These are the bad results of vibration, okay? Well, none of these are desirable. Wear, fatigue, and noise. So we try to prevent the vibrations, but there are some good applications of vibrations also. Just keep in mind that there is such a thing, good applications. Like vibrational conveyors, for example, or dental devices, or ultrasonics, let's say. But there are not that many. You might use vibrations for the benefit, but usually in the machines you try to prevent them as much as possible. But if you cannot prevent them, you want to confine them to an acceptable range. Okay. Let's go through some definitions because we need them. The periodic motion. A motion that repeats itself over the time is a periodic motion. For example, you might have a sine wave. I cannot prove it very well, but suppose that this is a sine wave. This is time, this is x of t. Okay. This period is going to be time interval at which the motion repeats itself. As you see, here you have a period t, and after that period, you get the exact same thing, the same sine wave once more. So this is t again. Once more, the same thing. Well, suppose that these are the same. This is t. So if the motion repeats itself, so this is a sine wave that is periodic, but the periodic motion doesn't have to be a sine wave. You can have, for example, this. You might have come to the same place, do the same thing, come to the same place. My drawing is not too good, but you understand. Do this and so that this is the period of the motion. T, this is the period. So this is also the T, etc. Okay. So it repeats itself with a certain time interval, and this motion is called periodic. Okay. The simplest periodic motion is, as I have said, is the sine wave. And the period is t. Now, let me just define a few more things. The transient means motion that changes in time. So transient motion is, for example, this would be a transient motion. It changes in time and eventually decays, for example. And it doesn't repeat itself anymore, okay? Whereas the opposite of the transient is the steady state motion. That is motion that repeats, which is periodic, that is. So, for example, a sine wave is, well, this might be, for example, well, I cannot go through that. This is steady state. It doesn't, over the time, it doesn't decay or grow up or anything. So that is a steady state motion. A motion can start as transient and then come to a steady state. For example, you might start as like this, let's say, and then the motion can settle at a steady state. So this part would be a transient part. Where there are transients that die out over the time. Eventually, this part is the steady state. So, for example, when you start a motor, in the beginning, it's, speeds up, and eventually it comes to a certain speed, and then it operates at that steady state speed. There might be some vibration or not, but it doesn't matter. The steady state is the motion that is steady, that keeps repeating itself. Okay. Frequency is an important concept. It is the number of cycles that is periods, that is, per unit time. Usually, that unit time is usually in seconds. So it is the units, the cycles per second, okay? Or we say it, CPS. And there is a name for that, that is Hertz. Hz is the name for this. And therefore the F, the frequency, is defined as the 1 over the periods, okay? 1 over the period, and that is the Hertz. To honor that German scientist, Heinrich Hertz. So it is the cycles per unit time is the frequency. And for example, the electricity in our network is either 50 or 60 Hertz. That's the most common application. But we don't use this Hertz concept, but we do use it. But in science, much more important is the circular frequency, which we call the omega. And this is omega and not W, as most of you call it. It's a Greek letter. And its unit is radians per second, okay? Now, F is 1 over T, but we want to measure the let's say, rotation or frequency in terms of, not in terms of seconds, but not in terms of, well, motion periods, but in terms of radians. So omega is 2 pi. Since one rotation is 2 pi radians, omega is 2 pi over t. This is an important equation. Just keep this in mind. Okay? And its unit is radians per second. Omega and hertz are related. Omega is simply 2 pi times f, of course. That's also obvious and important. Okay. Yes, since we are measuring sines and cosines in terms of radians, we have to use omega, not the f. But you can always use 2 pi f inside your sine or cosine function. But more common way is to use the omega. So a sine wave is, or a cosine wave is like a sine omega t, is something like this. This is t. This is, well, let's say x is equal to, this is x. This is a sign that changes over the time. Its period is the period at which the thing repeats itself. Omega, as you know, is 2 pi over t. And its amplitude, A is the amplitude, this is A, and this is minus A. It changes between plus A and minus A. As you see, A is the amplitude. Amplitude of the phase. So sine wave is something that repeats itself. A cosine wave would be, you know, it's a something. Cosine would be something that starts with a when it is equal to 1, not that is, when t is equal to 0, the cosine is equal to 1. The phase angle is the angle difference between two, let's say, well, it is sine or cosine, so let's call it waves. Let me try to draw this. Let's say that you have a t here. Let's say this is x. Let's say we have a sine wave. This looks like a sine wave. It is not exactly a sine wave, but let's have another one. It's not very easy to draw this. Okay, so as you see, there is a phase difference between them. They are very similar motions, but there is this amount of time difference. Let's call it tau. This tau is the phase difference, and the phase angle phi is simply omega times tau. It is the called phase angle. Okay. If you call the yellow line x1 and if you call the red line x2, you can write the following. For example, x1 would be some amplitude times sine omega t, whereas x2 would be, t is the time, by the way, if you are a sine omega t minus 5. There is a lag of phi angle, okay? Here we call that x1 leads x2 with tau. That is the time period. And the difference in phase is shown by that phi angle, which is given by omega times tau. Okay. I will take a break soon, but let me just finish this. Amplitude is the maximum value. Let me just write this maximum value of a sine wave. Amplitude, phase angle, frequency. These are very basic concepts. Okay, well, at this point, let's take a break for a while. I will continue the next time. Did I start recording? Yes. Okay. Is what we call the simple harmonic motion. This is motion that can be expressed by a sine or a cosine. Sine and cosine in this context is the same function. Or a linear combination of them. So, for example, x1 of t, if this is, let's say, a sine omega t. Okay. If x2 of t is the cosine omega t, these are harmonic motions, simple harmonic motions, because they contain a single frequency. For example, x3, if you add them, x1 of t plus x2 of t which is a sine omega t plus b plus b cosine omega t. As a matter of fact, we can express this as we will see, is a sine omega t minus a phase angle. Okay, all are simple harmonic motions. Okay, that is, they can be expressed by a single sine or a cosine wave with a certain frequency, or a sine wave with a phase shift. By the way, remember that sine and cosine are very related functions. Sine omega t is simply cosine omega t minus pi over 2. Okay. Actually, I think it is plus pi over 2. And cosine omega t is sine omega t minus pi omega t. Okay. There is only a phase difference of pi over 2, which is 90 degrees between phase sines and cosines. So for our applications, you can use sines and cosines, well, interchangeably, let's say. As long as you know the sign difference, you can, phase difference, you can use them. Anyway, sines and cosine functions are extremely important in vibrations. They are the fundamentals. Now we can now go to vibrations. Vibrations can be free or force. Okay. Well, we will look at free vibrations most of the time in this course, but also to forced vibrations. Free vibration is more easy. This is no external forces. But how can you have a vibration with no external forces? You can, for example, have a vibrating system. You can push it, give it an initial condition, and it can oscillate like a pendulum clock or something. Okay. No external forces, let's say, or disturbances. Here you have the external forces are the cause of vibration. Let's look at the free vibrations first. So, for example, the simplest thing, I'm sorry, is a mass spring system, as you know. You have a mass like this, mass and a spring on a, well, let's say smooth floor. What can you do? You can take it and displace it an amount of, let's say, like this. So that the spring is extended, and so that this initial difference is, let's say, x0. x0 being the initial displacement. Which we will call the initial condition. Now, if you do this from here, let me try to draw the motion, if you have a hand pointer or something, the motion that you are going to obtain is going to be something like this over the time. Let's say this is X. So you will start from here. Let me try to draw it in another color. So it will oscillate over the time. So what will that your thing do? It will do the following. Let's say that you have no friction, so that your mass is going to go back and forth. If I stop this, I will. And so on, okay? So the important thing is there is no external force here. Only the initial condition. You see the initial displacement is x0 here, and it starts from x0 and it continues to oscillate like that. Now this motion is actually, it can be expressed in terms of a sine wave or a cosine wave. It has a certain period, as you see. It repeats itself with a certain period, t. This period has to do with the system parameters. Since the system is free, the frequency of vibration, let me write it here, frequency of free vibration is called the natural frequency omega n. And as we will see, omega n has to do with the system parameters. It's 2 pi over t, obviously, period t being the period, but this is equal to root k over m. This is what we will see later on. Okay, root k over m is the natural frequency, and its unit is radians per second. The frequency of oscillations of a system, of a mass spring system like this one, simple harmonic motion, is dependent on its system parameters. For example, a similar thing would be a pendulum, like this, pendulum clock, like here, with an angle of theta, if this is the pendulum. This is L, this is G. There might be a mass of the pendulum, but it doesn't matter. The natural frequency of a pendulum is G over L. Okay, this is a N, not. So the natural frequency is the frequency of free vibrations of a system, and it is not. It is dependent on the system's parameters. Okay, so the pendulum clock oscillates just like this, and it depends on basically on its length. Longer the length, lower the frequency. Okay, so free vibrations are the vibrations due to initial conditions of a system. That is, you leave a system and let it oscillate. It oscillates at its own frequency. Now, the natural frequency is extremely important in a system because it has to do with the forced vibrations as well. This is what we have talked about, is the free vibrations. Whereas the forced vibrations is the second kind of vibration. This is motion due to external forces. If there are external forces acting on the system, for example, f of t equals sometimes like f0 sine omega t, let's say. This is harmonic. This would be harmonic forcing, for example. This is example, of course. Okay. Now there is a concept called resonance in vibrations, which we make a great deal of it. We will study this in detail later on, but let me just give the definition here. It might not be very clear, but it will be clear later. If the frequency of the external forcing, for example, this omega, coincides with natural frequency omega n of the system. We have the phenomenon called resonance. In the case of resonance, in this case, the amplitude of the motion grows, but actually, if there is no damping, it grows indefinitely. That is, the motion becomes, well, amplitude becomes infinite until the system breaks down. This is a real effect, and it is due to the fact that in the resonance, you keep on adding energy to the system. So in the case of resonance, we have the following. We will study this later on, but let me just give you the idea. Let's say this is M, this is K. You force it, F equals F0 sine omega t, and this is X, okay? Now the omega n is root K over M. This is the natural frequency, okay? Natural frequency. And if omega, which is this omega, equals omega n, then we have resonance. That is, in that case, the amplitude x of t will go to infinity as t goes to infinity. Okay. As t increases, x of t is going to be like this, t versus x of t. This is x. It will start from here. And so on. It will grow up, and eventually, probably at some point, the structure you have is going to fail. Okay. Of course, it is undesirable. It is not wanted, undesirable. So you try to avoid the resonance, and that's one of the important points in vibrations. But we will come to that later on. Okay. Let's go on. How do we model the vibrating system? So the modeling is an important issue. But vibrations can be defined as cause of vibration is the interchange of kinetic energy and potential energy in a system. Okay, so you have well, a system that oscillates between maximum kinetic energy and maximum potential energy, and that is the one interpretation of vibration. As we know, for the kinetic energy, we have the masses or the inertias stores kinetic energy. Okay, whereas for the potential energy, we have springs stiffness, let's say, or springs stores potential energy. Well, we don't have to have real springs, okay? All the elastic objects, well, can store strain energy, which is a form of kinetic energy as well. Sorry, potential energy as well. So we usually model them by some kind of a spring. Now there is a third kind of thing, which is the dissipation, which is also important for us. So there is damping. This damping dissipates energy. So we will try to model the vibrating systems by including these three effects: kinetic energy, potential energy, and the dissipation, energy dissipation. Okay. Well, let's start from the kinetic energy. Well, what do we have? We have a mass, obviously. You have a force applied to it, and the mass gets displaced an amount of x of t. Let's say this is m. Well, this is not the only way to store kinetic energy, by the way. This is the translational version of this. The equation of motion here is F equals ma, as you know, which is equal to m x double dot, as you know. Now, the kinetic energy that is stored here is 1 over 2 mv squared, as you know, which is 1 over 2 squared. But this is translational. Well, there is one more thing, and that is the rotation. You might have, this is not too good. You might have a disk that is rotating like this, about an axis like this. You might apply a moment m to it, and this can rotate with omega, which is equal to theta dot, as you know. The moment applied to this disk has a moment of inertia of I, let's say, I times alpha, which is I times omega dot, which is theta double dot And the kinetic energy in a rotating disk would be 1/2 I times omega squared, or 1/2 times I times theta is some angle from, this is theta. So this is the rotational rotation. In terms of potential energy, well, we have springs, as we know, like this one goes with x1, this one x2. There might be, well, this spring can be in tension or compression with the same force usually, and that force is given by the spring constant k times x2 minus x1. And the potential energy here would be 1/2 k x1 squared. But you might have a similar thing for the rotational spring. For example, a shaft can be considered as a rotational spring. Let's say this rotates with theta 1, this rotates with. This is a torsional spring, KT, let's say. So this is T, and this is the opposite T. T would be equal to the torque applied is K2 times Q minus theta 1. And the potential energy here would be 1/2 kT squared, as you know, all these things. Now, this is kinetic and potential energies. There is also the third element, which is the damper. You might or might not have seen this. This is like a shock absorber. Okay, this is the way we draw it is like this. It is like we draw it like a shock absorber actually. Something that, a piston that moves inside a container, so that, let's say that there is oil, it's like there is oil in it. On one side, you have this, on the other side, you have another one. So this has to do with velocities. Let's say this is V1, and this has V2. V1 is x1 dot, V2 is x2 dot. Okay. Both ends have different velocities, and there might be a force acting on this. Again, either compression or tension. F would be equal to some damping constant times the difference in velocities. Okay. This is the translational damper. There might be a rotational damper as well. Actually, just as here you can have a rotational damper, which you can draw here, which I don't want to. This can be a rotational damper, for example, in which you have so that the torque is equal to Here you have dt, let's say dt times beta 2 dot minus. So there are always rotational, or we can write this as dt times omega 2 minus same thing. Now here the power dissipated is important in dampers. The power dissipated which we will call the power script P dissipated. There's the force times the relative velocity in these dampers, and this would be forces V times V2 minus V1 times the relative velocity is V2 minus V1. So it is V V2 minus V1 squared, or V1 minus V2 squared. It is the same thing, okay? The dissipated power is always, it's a quantity that's greater than 0. So these are the basic elements which we use in order to construct our vibrational equations, the equations of motion. Now we will go on with deriving the equations of motion. The equations of motion for vibrational systems we will use this abbreviation EOM in short. Well, the equations of motion are now, they are second order differential equations, okay? You have taken a class in differential equations, and if you have wondered why you are taking it or where it will be useful, it is going to be useful here, okay? In vibrations, our equations are not normal algebraic equations, they are the differential equations, okay? And this is probably the first time in which you will be really solving differential equations. That is, these equations dominate the motion of the system under every condition. Once you solve it, you get how the motion, how the system is going to behave. Well, how to derive these equations, how to obtain these equations, let's say. There are two ways of doing this, which are both useful. One is the classical Newton's laws. In which you draw free body diagrams for each mass and inertia. Then apply, let's say, summation of forces is equal to mass times acceleration. Summation of moments is equal to I times alpha for each mass and inertia. That is the classical way of writing the equations of motion. From here, we are going to get the differential equation, not just the algebraic equation, okay? That's the difference between dynamics and here. And the second is possibly the a more direct approach, the energy method. And the students like this method more than it seems Newton's method because it's kind of simpler. The total energy of the system is, as you know, is the kinetic plus the potential energy. What we do is we write take the derivative of this energy, and this will be equal to the power in minus P power dissipated. So, which means that input power minus the dissipated power is the net power input to the system. And this gives us the equation of motion. In many cases, this energy method is probably simpler to obtain using the energy method. It's simpler to obtain to get the equation of motion. Let me give you one example using both methods, and then I will probably stop because there will be no time left. Let's say that we have a system with a spring, a damper, and a mass. Spring constant is K, this is B. Well, in real life, we don't have such systems, okay? This is like a toy system, but this kind of system basically represents a large number of vibrational systems can be represented by a mass, by a spring, and by a damper. Damper represents the friction, viscous friction, and well, F represents the forcing, spring represents the elasticity in the system, and the mass represents the mass. So we will try to derive the equation of motion. And let's look at the Newton's method first. So we draw the free body diagram of the mass. So what are the forces? Obviously, there is F of t. The spring force is in the opposite direction, Kx. The damping force is Bx dot. Okay. There is mg downwards, and also there is the normal force upwards. We are not really interested in the motion in the y direction because there is no motion actually. This is m. Now the sum of the forces is equal to, well, the forces are F of t in the positive direction. Negative forces is Kx, negative is Bx dot. That's all. These are all the real forces. This is equal to Ma, but Ma is equal to Mx double dot. Okay? So our equation of motion, if you collect the terms, Mx double dot plus Bx dot plus Kx equals F of t. By the way, what is dot? I'm using these dots here. X dot equals dx dt. X double dot will be e squared x dt squared, etc. Okay. This dot notation means time derivative. So this is the equation of motion. It's a second order differential equation, as you see. Okay. Well, I could get that box out of this. Let's try it again. Okay. It's a second order differential equation that represents our system. Well, the same equation could have been obtained by the energy method. in which we don't have to draw a free body diagram. We just write the energy. The total energy is kinetic plus potential energy, which is 1/2 mx dot squared kinetic plus 1/2 kx squared. Okay. The input power is F times x dot, right? The force times the velocity is the input power. And the dissipated power is dx dot times x dot, which is dx dot squared. So what we do is dE dt is we take the derivative of the energy, time derivative. So you get this 2 comes here and cancels 1/2. So m x dot x double dot chain rule plus this 2 comes here k x dot is equal to p in minus p e, which is f x dot minus b x dot squared. And we have this side, left hand side, right hand side, they all have x dot terms. This one, this one, this one, and let's say square term like here. And bx dot is left here. You can carry it out to the other side, so you get mx double dot plus bx dot plus ax. The same result. Anyway. Okay. Do you have any questions? I tried to make a basic introduction to vibrations here. Well, we will continue this after the midterm.
Hocam, is this topic included in the midterm exam too?
No,
The vibration.
no, it's not included.
Okay hocam.
In the midterm, you have the gears and the static and dynamic force analysis. Okay?
Okay hocam.
Hocam, do we need to restudy the first chapters for the midterms?